Hello everyone, and welcome to our first video, an introduction to OFDM-SPM. Why OFDM-SPM? So first of all, I think it's important that we talk a bit about the evolution of wireless networks. As we all know, wireless communication technologies and telecommunication systems in general have come a long way. They've seen continual growth and improvement. As a matter of fact, the number of devices connected today in any one building or the amount of data being transferred at any instance is rather massive. We've come all the way from the radio to the television to what we have today. Uh, During all this improvement, a core technology which actually enabled much of this is OFDM, especially in wireless communication technology, which means orthogonal frequency division multiplexing. This is a multiplexing technique which basically uses the orthogonality between its subcarriers in a symbol. It uses the orthogonality to be able to squeeze in more subcarriers within a given frequency bandwidth while minimizing interference between them. As a matter of fact, there is zero interference between them as they are orthogonal. So this was basically a core technology which enabled 4G and 4.5G communication systems. It's highly thought that it will be used in 5G communication systems as well. And well, as technology keeps progressing, we're bound to have 6G and 7G communication systems, but we are uncertain, however, of what technology will be leading them. So, as we said, we've come a long way, but is this enough, however? Why do we need all this? Have we been able to meet the requirements by most of our applications today, or the applications which will be coming in the future? Well, apparently not quite. 5G technology, even though it will meet a lot of requirements by a set of different applications, however, it couldn't meet them all simultaneously. What 5G did was it would cater to a set of specific requirements and neglect a bunch of others, thus setting basically something similar to use cases, as in this would use this technology and this would use this technology, depending on what it needed most. However, 6G technology and the applications it will require will be a bit different in that it will require a lot of things simultaneously. This includes high spectral efficiency, data rates, low complexity, and good reliability. For those of you who don't know what that means, well, high spectral efficiency is basically means how efficiently can we use a given spectrum of bandwidth in terms of data transmission. Data rates also means how much data are we able to transmit. Low complexity, when we say this, we're referring to computational complexity as well. We know that currently millions, if not billions of devices are using wireless technology, and some of them are very small, especially with the IoT coming up right now. We have very small devices which don't want to use a lot of computational complexity. We don't want to use too much power, which is why low complexity is going to be a big advantage. And good reliability simply means that the data we transfer is reliable. It's received in a correct manner. It's not received in error. In the end, if you're transferring erroneous bits or erroneous data, then what's the point of transferring it at all? So some of the 6G applications which are pushing us towards better telecommunication systems currently are expected to include telemedicine, mixed reality, augmented reality, haptics and brain-machine interfaces, real-time gaming, high video streaming, and much more. So one of the main issues being addressed in novel telecommunication technologies is, well, data rate. So how has this issue been addressed? What are the issues? What are the approaches that have been taken? Well, a very classical approach to take is actually by infrastructure. However, improving infrastructure. However, this can be costly, both in terms of time and money. Other people have thought about, well, why don't we try to use perhaps more advantageous multiplexing techniques, which might be better to use than OFDM? Some of the current research has been on NOMA, MIMO, in-band full duplex. These are other multiplexing techniques. Other people, on the other hand, have seen that given that OFDM is implemented in the standard, it has a set of advantages which we can't deny. In that case, why don't we just try to build upon it? Why don't we just improve it? So a set of techniques which have which were introduced have actually added a third data carrying dimension to OFDM. And in my opinion, that's actually very smart, because what it does is it takes your classical OFDM symbol right here, utilizing classical OFDM technology. And what it does is it says, okay, so we know that this is an OFDM symbol and we're already transferring data in two dimensions right here, but what can we add to this? What can we change in this to add more meaning to it? How can we change some things such that it implies that we're transferring data, that we're encoding data into it? And well, what most of these techniques have done is actually change the characteristics of the subcarriers of the OFDM symbol. So some of these techniques have done this to the indices of the subcarriers, some of them by changing the number of subcarriers in a symbol. And this is actually where the idea of OFDM-SPM comes from. As the name suggests, SPM, subcarrier power modulation. We thought, why not change the power? Why not change the power of an OFDM subcarrier right here? Instead of making them all have the same power, let's differ there. Let's make them have different powers and give that meaning. Let's let that annotate a bit or two, So that's the idea behind OFDM-SPM. And as you can see, it's rather simple, rather intuitive. However, will this work? There are certain requirements which you must meet, which brings us to our criteria, actually, our performance criteria of a modulation scheme. So current day performance criteria include spectral efficiency, which we've spoken about before, energy efficiency, how much energy is it going to use? Is it going to use the same amount of energy that conventional OFDM uses? Does it use more? What about flexibility? Does it offer the user or the application flexibility in what he can do with this scheme? Computational complexity. As I said, we don't want them to be computationally complex because that simply uses more power. And for small devices, we don't want that at all. Reliability. Will this scheme be able to transfer a lot of data while maintaining that the data is transmitted and received in a manner which is not erroneous, in a successful manner? Are the gains scalable? Scalability is very important. If we can apply this scheme to a lower order system with low order modulation, such as BPSK or something like that, will we be able to apply it to the larger scale in Wi-Fi systems? This is very important, where things actually matter. Does the system have any inherent faults? Does it come with any constraints that you simply have to deal with? All of these determine how well we can perceive, or how well we can think of the performance of a novel modulation scheme. So speaking about these criteria, this brings us to why OFDM-SPM. Why do we think that OFDM-SPM will be a suitable modulation technique for future 5G and 6G communication systems? Well, OFDM-SPM is able to achieve high spectral efficiency and data rates. It offers shorter transmission times, such that it uses less resources in the time domain. It has low complexity. It can even reduce the complexity if necessary. It uses no extra energy and can be even more power efficient than conventional OFDM. Keep in mind that all these comparisons that we're doing will be done with reference to conventional OFDM. That's the standard that's been taken, and that's how the comparison has been done with other schemes which have introduced third data carrying dimensions. So, and last but not least, OFDM-SPM offers flexibility by allowing different power allocation policies. So we have a brief idea of how OFDM-SPM works, the basic working concept. And as we understand, we claim that it has a certain number of gains. So, but how does all this happen? Why does this actually work? Well, let's see in our next video. So please stay tuned, and we'll see you soon.